Aloha and good evening, everyone. We will be starting our talk in about 2 minutes to give people a little extra time to join us. So at about 5:32 Hawaii time, we'll start the talk. You're welcome to share the URL with your friends, family, and colleagues. The easiest is for them to just go to youtube.com/UHIFA to watch the live stream there. And it'll also be available there after the show or after the presentation. Thank you. Okay, aloha and good evening, guests. Welcome to our fourth and final Hawaii Webb Connection talk. My name is Roy Gal. I'm going to be your host for the evening, and I'll tell you a little bit about our speaker and his presentation, and then he's going to take it away. So, as I said, my name is Roy Gal. I'm your moderator. The speaker is Chris Ashall. He's a postdoctoral fellow at the Institute for Astronomy. Before I tell you a little bit more about him, I'd like to encourage you to sign up for our newsletter at the URL on the screen. And if you don't already, please follow us on social media. We're UHIFA pretty much everywhere. It's a great way to get information about our public presentations, events, and astronomy news. If you're here in Hawaii, now that many of the COVID restrictions have lifted on Oahu at least, we have begun doing public events, so we'll be sharing more of those as we begin to plan them. Also, if you have folks who are interested in this talk but cannot make it, it will be available on our YouTube channel afterwards. If you have questions, please save them for the end of the talk. You can use the Q&A or chat functions in Zoom, or if you're joining us on YouTube, you can just put the questions into the comments section and I will be monitoring them to read them out to our speaker at the end of his talk. But you can post the questions anytime. So our speaker today is Chris Ashall. He came about 2 years ago to the Institute for Astronomy. He received his Bachelor of Science in Astrophysics. I will leave the pronunciation of that university name to Chris. And then got his master's at University College London and his PhD at Liverpool John Moores University, also in England. He moved from there to sunny Florida, where he was a postdoctoral fellow, and then he decided he'd like to get even more tropical and joined us here in Hawaii in 2019. Chris specializes in time domain astronomy. That means that looking at things that change with time. And we do a lot of that at the University of Hawaii, everything from asteroids that move to stars that vary to supernovae, stars that explode. And that is actually Chris's specialty, the science of supernovae or exploding stars. And that's what he's going to tell us about tonight. He's worked on both the observations and theory of supernovae, especially focusing on what they look like in wavelength ranges from the ultraviolet to the mid-infrared, using ground and space-based data. And he's here with us in Hawaii working on the roboticization of the 88-inch telescope on Mauna Kea, which is now over 50 years old, but is constantly being upgraded. So with that, I'm going to ask Chris to take over the screen and begin his talk. Thank you.
Hi. Let's see. Oh, screen sharing just stopped. Okay, 1 second. Okay, thank you. I hope everyone can see my screen. Okay. Thanks for the great introduction. I'm Chris Ashall, as been said. I'm a postdoc here, and one of my I work on exploding stars. And one of the things I'm working on right now, which I'm very excited for, is the James Webb Space Telescope. So right here on the right-hand side, you see this amazing image taken of a supernova remnant, and this is an exploding star taken thousands of years after the explosion. On the left-hand side, you see a very recent image of JWST, all folded up and ready for this launch. So today I'm going to tell you a bit about what a supernovae is, what are supernovae, then I'll talk about the James Webb Space Telescope, what we're going to do, its journey to its launch and its launch. Then I'm going to talk about the projects we're leading here in Hawaii. But first I'm going to start with this, something a little bit closer to home. So blood, glass, the Earth's crust, batteries, graphite, and steel. What do all these things have in common? There's something I'm going to get back to at the end of the talk, but it's really something that maybe you can think about while I'm giving this talk. What's so interesting about all of these things? At the end of the talk, I'll tell you what I think is so interesting about them. But yeah, so blood, glass, the Earth's crust, batteries, graphite, and steel. So anyway, what is a supernovae? So a supernovae is the death of a star, but it's the explosive death of a star. And it's luminous, it's so bright, it's much brighter than the sun, 500 billion times brighter. And there's two types of supernovae, one called a core collapse and one called thermonuclear, or type 1a. But before we think about what is a supernovae, we must think how a star works. So stars that are massive, more than 8 times the size of the sun, they're in balance. In equilibrium. The gravity is pulling it in, and the thermal pressure from the burning is pushing it out. So this keeps the star in balance, and the star is made up of mainly hydrogen and helium. And the hydrogen burns, and then the helium burns, and over time, the hydrogen burns to helium, the helium burns to carbon, the carbon burns to oxygen. As you get to heavier elements like silicon iron, it can no longer burn. And this thermal pressure is no longer enough, because it can't burn, to match the gravity. And it becomes unstable, and the gravity overtakes this thermal pressure. And because of this, the star collapses in on itself. And within less than a second, something that is 8 times the mass of the sun collapses into about 11 kilometers wide. So within less than 1 second, all this mass goes very slowly, very quickly into the center, to this core. And it collapses in, and then because it collapses so quickly, it rebounds. And it's this huge reverse shock and explosion. And all this energy and all this material from the star gets thrown out into the universe at 30% of the speed of light. And it's 500 billion times brighter than the sun. And that's a core collapse supernova explosion. And it leaves behind something very dense called a neutron star or a black hole. And that's one of the most luminous events in the universe. And this happens when massive stars die. The other type of supernovae comes from white dwarf stars. Now, white dwarf stars are very dense. They're about the mass of the sun, but they're about the size of the Earth. So 1 teaspoon of a white dwarf star on the Earth would weigh as much as an elephant, around 5 tons. And rather than these white dwarf stars being balanced by pressure from the burning in the center, they're actually balanced by something called electron degeneracy pressure. And this is something that comes from quantum mechanics, specifically something called the Pauli exclusion principle. But essentially, it just means electrons cannot be in the same energy state in the same volume, which means when they're all crammed together very densely, there's a pressure pushing back against this. And it's this pressure which balances against the gravity. And Chandrasekhar, the famous physicist from the 1930s, calculated that this degeneracy pressure is good, and it balances the star in equilibrium until you get to about 1.4 solar masses, above which the Chandrasekhar limit is reached. And when this limit is reached, the star becomes unstable, and burning starts, and an explosion happens. And this explosion is also 300 or 500 billion times brighter than the sun, and ejects energy and material into the universe at 30% of the speed of light. And there's a few ways you can make Type 1a supernovae, but two of the most popular ways are if you have two of these white dwarfs and they spiral together. And over time they spiral and they get closer and closer and closer. And then they spiral in so violently they merge and then they explode. Or you can have a white dwarf. And I should say these white dwarfs are composed of about 50% carbon, 50% oxygen. You have a white dwarf and it's got material that gets accreted onto it from a different star, a star like our sun or a brighter star or a redder star. This material gets accreted onto it and it starts to approach this Chandrasekhar limit. And once it approaches this limit, it can explode. And there's many variations within this picture and details of the physics, but this is the general idea of what Type 1a supernovae, or thermonuclear as they're called. And what's so amazing about these supernovae is that they always explode at the same brightness. And when something explodes at the same brightness, it's really easy, or same luminosity, it's really easy to figure out how far away it is. Because we know if it's very bright in the sky, it's got to be close by, or if we see it very faint, it's very far away. And with that, we can calculate what the distance is. So, and these are known as standard candles or cosmic distance rulers. And Type 1a supernovae were very important because they were used to figure out that the universe is actually accelerating away from us. And this led us to the winning, to the winning of the Nobel Prize in 2011. But that's for a different talk. But it's absolutely amazing. There are amazing measures to look at the universe. But today I'm going to talk about the physics of the universe. So how do we find supernovae? So essentially we play spot the difference. We have surveys, we have telescopes, and they look at the sky every night. And once they've looked at the sky, they take a beautiful image of a galaxy like this one. This is M101. And they take this picture and they say, okay, this is a galaxy. It's got spiral arms. It's got a core. There's stars around. But then the next night, they look at this image. And they say, hang on, there's this extra dot. This is a transient event. We don't know what it is. Could be a supernova. So we do this all over the sky. And then essentially, we find a supernova. So for example, if you look at this left image here, in this circular dot, you'll see there's the date going along. As it goes along, there's nothing. And then a supernova appears. And we can follow this and its brightness for over years or months, days, years. And an example here, you'll see there's another example on the right-hand side. Here's a nice galaxy with a core, some arms, which are all made of there's stars all around. And if you notice up here, when I play this, supernova appears over time. And what you see here in this plot is that this is how bright it is, and this is how much time passes. So a supernova is brighter, it goes to become very luminous and then fades over time. So it takes about a couple of weeks to become very bright and then fades over time. And this brightness is powered by radioactive decay. And then when we look at these events, thousands of years later, we get what I think are some of the most beautiful images in astronomy, supernova remnants. And these are composites of when we look at it in the optical and the X-ray. And you can start to see how these supernovae were, very symmetrical and making small clusters and instabilities into the medium around. And these are three close by remnants called Cassiopeia A, N49, and this is the Tycho supernovae. So it's great that we can go away and we can look at how bright a supernovae is and how it changes over time. And we say, oh, it gets brighter. We can use them to measure the distances into the universe. But if we want to look at more than that. We want to look at the elements they make. And to look at the elements they make, we need to understand what a spectrum is. So we want to look at these different elements and different ions. So what is a spectrum? A spectrum, you get taught in school that the white light goes into a prism, the prism diffracts the light, and then it goes from red to blue. So this is shorter wavelengths to long wavelengths. And this is basically gives us the spectrum of light. And Hawaii is the rainbow state. You see so many rainbows, and you can see that here on the right-hand side. Beautiful picture of Waikiki with Diamond Head in the background. This amazing rainbow going over the back. And in our eyes, because we see in the visual, we see from red to blue. But in fact, if we had different sensors in our eyes, we would say there's actually light. We'd see it in the ultraviolet, and there's more light further across into the infrared. And that gives us lots of information that is missing with our normal eyes. So when we see a spectrum, like a rainbow, this is where light gives off, something comes from a source, and you see a continuous spectrum. But if this light is to pass through a cloud of gas, or in our case, a supernovae, so this will be the core of the supernovae, and the light will pass through it, and we're looking at it from the other side, this light will be absorbed by certain elements and molecules on ions. And then we get these absorption lines or dark lines. And this is where the light is absorbed by these elements and ions. And then if we view it from a different side, so the light isn't from behind, we might see that these ions, which have previously absorbed light, will then emit light. And these are called bright line spectrum, and these are emission spectrum. And this is very important if we're going to understand elements within the universe, and especially within supernovae. So this might be what a spectrum looks like before it's reduced. This is not of a supernovae, but you see here that there's the red side and it goes to the blue. So this is higher energy blue light than the red light. These are longer wavelengths. And going off to the blue, it goes to the ultraviolet. And going off to the red, it goes to the infrared. And each of these different lines come from elements. And what we can do is we can reduce this sort of data on the computer with special codes we have and get scientific plots like this. And this is the spectra, for instance, an absorption spectra. So this is the wavelength, and then this is how bright it is. So you see there's these different dips, which are the absorptions. And in the absorptions, we have silicon, sulfur, iron, magnesium. And this is a type 1a supernovae. And this is the optical. So then we can go off to the UV over here or the infrared over here. And there's all these different elements and lines and ions available to look at. And then we can look at something here. And this is what one of the bright light spectra or an emission spectrum. And there's oxygen, calcium, carbon, cobalt, all in these spectra. Now, when we look at supernovae, we have amazing data in the optical. We have quite good data in the ultraviolet, but when we go to these longer wavelengths, the infrared or mid-infrared, the data is very sparse. And what's interesting about different wavelengths is they contain different ions, different elements. So if in a laboratory in atomic physics, there is not a line from an element in the optical, we won't be able to see it if we take optical data. We need to go to these other wavelengths. And what's great about JWST is it's going to these much redder wavelengths. So we're going to be able to get information about elements and ions that we didn't before. And that's really good. So that's really exciting for the future of JWST. So it's going redder than we've ever gone before. And redder means longer wavelengths and different areas of physics. So all the data is new. So next, I'm going to talk a bit about the actual telescope. So James Webb, when did it launch? In 2007. Well, that was the plan. Didn't go too well. So the idea was for it to launch in 2007, but in 2005, it had a major redesign. And after that, it was built by roughly 2016, but tested for many years and improved. And then about 5 years later, we're ready for this launch. It's going to come very soon. And this telescope is the most expensive space observatory ever built. It cost $10 billion. And this is a beautiful picture of it taken the other week. And this was taken in California. And you can see it's got 18 mirrors, and they're all made of gold. And interestingly, they're made of gold because gold reflects the infrared better than silver. And then you've got along here, this is a space, the heat shield. And this is basically the back of this is going to block all of the sun's light, the Earth's light, the moon's light. So this takes very cold. and can look into the distant universe. So, here you can see the sun shield, and this is the part of the telescope folded up with the mirrors. So this is looking at it from the back, and here, we're looking at it from the front, but it's actually folded up. You see there's 3 there. So 1, 2, 3, 1, 2, 3. So this will fold out to make this beautiful mirror that's 6.5 meters across. And the secondary mirror is here, and you can see the size of it compared to a human. It's a beautiful thing. So when does this launch? Well, the launch is imminent, 22nd of December. So it's taken decades to get to this point, but this was taken, I took this screenshot about an hour ago. So 13 days, 9 hours, maybe 8 hours, 19 minutes and 59 seconds roughly. So that's how long we're waiting. We waited years, but now we're here. And, most people have said they waited a long time, but for me, in 2007, I was only 16. I would not be able to use this telescope. So for me, the delayed launch has been a blessing in disguise. It's been very exciting. So we have the telescope. It's built. It was in California. But how do you move the most expensive space telescope? You can't just put it on a plane and take it over. You've got to be careful. The answer is you do it very secretly. There was a real worry about pirates wanting to hijack this thing. You get a huge ransom for a $10 billion telescope. So you got to do it extremely secretly. So in the middle of the night, NASA, packed up JWST into this special case. Everyone wears hazmat suits, make sure nothing infects the telescope, gets on it. We don't want any dust, any particles. And then it gets put in this amazing outer case. This outer case is put on the back of a truck, and it's driven very, very slowly out by the army to a port in Los Angeles. From this port in Los Angeles, it needs to make this huge trip down to French Guiana. Lucky for us, the Panama Canal exists, and we don't need to go through Patagonia. So it goes down the Pacific coast, up through the Panama Canal, around the Caribbean Sea, into French Guiana. And it landed at the Port de Paracabo in French Guiana. And it was on this boat, this ship. This is the only telescope, the only thing on this ship. And here it is landing, docking. And then once it's docked, they get it on the truck, and they take it off to the European Space Agency spaceport at Kourou. So here it is arriving at Kourou. And this is the example. This is not the rocket that it's going to go on, but this is one of a similar type. But okay, we have JWST at the launch site, but how do we get it into space? Well, the answer to this is we get it in very carefully. This is the next biggest thing in astronomy. We've been waiting decades for it. It costs $10 billion. So it gets lifted off, moved very carefully over into position, and put up right on its stand. And this is how it will be launched into space. So it's going to go on the European Space Agency's Ariane 5 rocket. And JWST is going to sit on the top here. So it gets put in the top component as a core component, 2 boosters. And then this actually was a photo taken 2 days ago. And this is not the rocket that it will go on the left. This is an example. But this is the actual core component right here. So it's very exciting to see this. And here's an example of the Ariane 5 taking off. Not obviously JWST, but this is what it's going to go through in 2 weeks' time. Amazing launch, the power of this thing. But it's a very successful rocket, and it's been very successful in the past, so I think it's going to do great. And then it'll be one of the most nerve-wracking days of my life. But once it gets launched, that's not it. JWST is the most expensive piece of origami ever built. So obviously it's so big, it can't just go up in one piece with a 6.5 meter mirror. There's just no rockets built like that. So it has to go to space and then spend a month unfolding. So you can see here that this month, it has to deploy the structure, open the sun shield, tension this sun shield, unfold the secondary mirror, which is up there. Then it has to fold out the side. And then that's 1 month later when it's in its orbital point. And then from that, it can then start to cool down and then think about taking images. But why are we so excited about JWST? Well, many of you know the Hubble Space Telescope. And when you think of all the beautiful images you probably see on the news, on the TV, it's always of Hubble Space Telescope images. And Hubble was 2.4 meters. And that brought us into a whole new era of astronomy. Now, if we look at JWST, it's 6.5 meters. The light collecting area is so much bigger. So that means you can get so many more photons, you can see so much further, you're so much more sensitive. And Hubble observed from the ultraviolet just into the infrared, which is very interesting. We saw things we never realized we see, like the deep field images. But what's amazing about JWST is it observes from the infrared to the mid-infrared. And this is so good because we can see the first stars, the first galaxies. When you look back to the beginning of the universe, the light is stretched because the light had to come all this way. The universe is 13.8 billion years old, and the first light from these stars comes 13.5 billion years ago. So even though it might be emitted in the UV or in the optical, it gets stretched. So when we observe it, we're going to be observing it in the mid-infrared. So we can see the first galaxies, the first stars, all forming. We can see the very early first bits of light in the universe. And on top of this, when we look back, we might see things we don't expect. It's going to be spectacular and very exciting. So when we look at the Hubble primary mirror compared to a person, that's the size of it. When we look at JWST, it's huge. It's much, much bigger. It's going to give us a lot more information. So what projects are we going to be working here in Hawaii? Well, we're going to be using Supernovae, but let me tell you, how does one get to use JWST? So Space Telescope, which is a part of NASA, which is in charge of all the astrophysicists, they say, please write a proposal. We're going to launch JWST. So you go away, you get a team, you write a proposal, and then they say it's delayed. So you go and do some other science. Then they say they're going to launch it. So you go, okay, you keep writing your proposal, you get some more scientific ideas, then you find out it's going to be delayed. And this happens for a few more times. Then one time they say, no, we're really going to launch it. So great. So you put together your team, make sure you're surrounded by smart people, and then you put it together, and then you put in these proposals, and they go off to scientists who review them, and then you see what happens. And then one day you wake up, and we were lucky enough to get 2 accepted proposals out of the 2 we put in. And these are the only proposals accepted from the state of Hawaii. So we're really fortunate to do that. And the first proposal we're going to look at is dust mass loss and explosions of massive stars in the mid-infrared. So that's core-clap supernovae. And the second one is mid-infrared spectroscopy of type 1a supernovae, the key to unlocking their explosions and element production. So when we think of core-clap supernovae, first I need to explain about cosmic dust for this first project. So what is cosmic dust? Cosmic dust makes up 1% of the stuff in the interstellar medium. The interstellar medium is the area between stars in galaxies. So in between the stars, there's the interstellar medium. It's 99% gas, 1% dust. And this dust can be composed of many things, including graphites, silicates. So graphites are carbon, silicates made of silicon-based things, and polycyclic aromatic hydrocarbons, PAHs for short. And these things are so important because they're the building blocks for complex life. A lot of what we're made out of is from this. We're carbon-based life forms. And one of the unanswered, unknown questions is, where does this dust come from in the early universe, also known as early universe cosmic dust. So we know locally that this dust might come from a certain type of star called an AGB star, but these stars didn't exist at the beginning of the universe. But supernovae did, core collapse supernovae did, especially from very massive stars. So what we're going to look at in this project is specifically two molecules. And these molecules are carbon monoxide and silicon oxide. So carbon monoxide is a carbon and an oxygen together. Silicon oxide is a silicon with an oxygen. And what's so important about these is that they only emit light at very low temperatures. And at these low temperatures, this is when we know that cosmic dust can form. So we think that supernovae might form this cosmic dust. But until now, we've never had the sensitivity or instrument or telescope or observatory to prove it. But if we find good emission of carbon monoxide or silicon monoxide, and we can work out the properties of that by comparing it to models we have, we can infer how much dust or if the supernovae are making cosmic dust. So with this project, we're going to obtain the first ever spectra of a core collapse supernovae with JWST. And these will be the best mid-infrared spectra ever taken of a core collapse supernovae. And with this, we're going to compare the silicon monoxide and the carbon monoxide to these predicted models we have with different masses and temperatures and velocities. And then we'll be able to understand if the supernovae here make cosmic dust. And then with that, we can infer whether the supernovae at the beginning of the universe, in the early universe, produced the early universe cosmic dust. And this is very important because, as I said, all this cosmic dust is important for the genesis of life and the organic molecules we're all made out of. And then the second project is to look at type 1a supernovae. So that's to obtain the first ever spectra of a type 1a supernovae with JWST in the mid-infrared. And that's really interesting because we're going to look, as I said, the mid-infrared. The reason we couldn't do this before is because we cannot see any of these spectral lines in either project. The mid-infrared is full of lines with all these elements that we haven't thought about, that we couldn't look at before. And this is a computer simulation. This is not data. But is there chromium, manganese, cobalt, nickel? We know type 1a supernovae make most of the iron in the universe, but there's still certain amounts of iron we think we might see in the mid-infrared. So we're looking for these, what we call iron group elements, these heavy elements. And with this, we can actually also infer the density of the burning and the explosion and at what masses they explode at. So with the type 1a supernovae, we're looking for these elements and different versions and states of the elements. And this is really important. And you might say, why is this important? Okay, it's easy to think why carbon is important, why the dust is important, why the silicates are important. But why are these small ions important, these parts of iron group elements? Well, it brings me back around to this. Blood. What makes your blood red? Hemoglobin, iron. Where's the iron made? In type 1a supernovae. What is a very abundant element in the Earth's crust? There's a lot of manganese in the Earth's crust. Where's that made? Well, we think we're going to try and prove that it's made in type 1a supernovae. That's hopefully what JWST will show us. Steel. When you're making metallic alloys, what do you need? Well, chromium and cobalt are used a lot in metallic alloys. Your car, your house, maybe your computer has all of these elements. Semiconductors. Think how many things have semiconductors in. And batteries. Your car battery is full of nickel, manganese, cobalt. There's many things. If your house runs out of power and you run off a battery, you probably need nickel, manganese, cobalt. They're all made in type 1a supernovae. And then glass is made from silicates, cosmic dust, made in core collapse supernovae. And graphites, well, that's carbon. The graphites are made in the core collapse supernovae, or that's what we want to prove. We're going away to look at these things. We think they prove that, or models say they go there. And for the first time ever, JWST is going to give us the chance to go and prove this. It's really exciting and it's really amazing. So you say the iron, the silicates, the manganese, the nickel, the manganese, the cobalt, the graphites, the chromium, the cobalt, they're all around us. And for the first time, JWST is going to be able to tell us a lot about this and shed light. And that's only because we can look at things in the mid-infrared. and these mid-infrared contain these spectral lines. But it's not enough just to use JWST. We're also lucky here in Hawaii that we have the best telescopes in the world on Mauna Kea, on the Big Island. And 3 of these telescopes, which are very important, are the Keck telescopes, Keck 1 and Keck 2, and the Gemini telescopes. So these are 10-meter telescopes, the Keck telescopes, the biggest optical telescopes in the world. And we need to follow our events, or supernovae, over a long period of time when they explode, to understand their evolution and their other properties, and especially to understand their optical and infrared properties at the same time as getting the mid-infrared from JWST. And Gemini is also an 8-meter class telescope, which is going to give us a huge amount of data in the optical and infrared. So altogether, we'll put a huge picture of these supernovae together to understand where these heavy elements which make us are from, which are useful all over the cosmos. So this is a really exciting time for astronomy. And I have my fingers crossed for the 22nd of December. I can't wait to see it, but I think a lot of us are very nervous, but very excited. So thank you for coming for the talk. And if we have any questions, I'll be happy to answer them.
All right. Mahalo, Chris, for this excellent talk. And Chris spoke to my heart right now because I'm at home hosting this talk, running off of a Tesla battery filled with nickel that came from these stars. So we're all connected this way.
We're trying to prove they came from these stars. That's what we'll do with JWST, hopefully.
Okay, so I have some questions coming in from YouTube. So one question is, what about elements like gold, silver, platinum, and other metallic elements? Are they formed in these kinds of supernovae?
That's a good question. So actually, so they're not formed in the type 1A. So there's the core collapse supernovae, and they're called all-process elements. And these supposedly could be formed in core collapse supernovae. So that's one of the things we're going to go and look away. So we know they're formed in neutron star mergers, which were recently discovered, where 2 neutron stars merge. But we don't know how common these are, and we don't think they existed in the early universe. However, core collapse supernovae did. So one of the parts of this project we're going to do is look for some of these all-process elements in the early universe or in nearby supernovae to see if we can see them, infer them that they were in the early universe from that. So core collapse supernovae could make some of these, but it's yet to be conclusively proven. That's what we're going to try and do.
Excellent. Now switching to a question on Zoom. Is there a plan to disseminate your findings within the broader community? It will be interesting and exciting for the general public to start learning about this.
Yeah, so hopefully as we go along, when the data comes in, especially we're using the telescopes here in Mauna Kea, we can do more talks about our results, put out press releases if they're interesting, and just any ways that people are interested, question and answer sessions, talks, press releases. Yeah, I'd love to teach more people about this research.
And I will say, I already talked to Chris and said that when he has some interesting results, we'll do a public talk on the science that came from it. So we do host Frontiers of Astronomy and other lecture series, which are available to the public, and we'll be advertising those. So keep a lookout for them. Next, we have another question from YouTube. Why is this not launching from Cape Canaveral, and why is it launching from French Guiana instead?
That's a very good question. I don't actually. So Cape Canaveral is a NASA. So I think this is the answer, but I might be wrong. This would be my guess. So the mission is a joint NASA and ESA mission, European Space Agency, and NASA are in charge of the build. And so some of the instruments came from Europe, but NASA are in charge of building and constructing the whole thing. And ESA's part of this was the launch. And in French Guiana, that's where the ESA launch facility is. There might be, so that'll be my answer, but there might be actually another reason that it's better to launch to L2, the second Lagrange point, from there. But seeing as they're both very similar in latitude or longitude, sorry, I think that maybe it's that, that ESA promised to do the launch and NASA promised to do the build. I'll have to check that one.
All right, thank you, Chris. And since you mentioned L2, that's a perfect lead into our next question is that where the telescope will be? And maybe you can explain what L2 is.
Yeah. Yes.
And there are other telescopes, satellites going to L2 eventually. So is there a problem with cluttering there?
I'm not sure about the cluttering, but L2 is essentially when you have three bodies in orbit, there's certain points, which means these bodies can stay in orbit of one another, say relative to one another. So essentially an L2 point is where is the other side of the Earth from the sun. So you have the sun, the Earth, and then the L2 point far out. And the advantage of this is that JWST will stay locked in orbit around roughly around the Earth with its back to the Earth, the moon, and the sun, meaning all of that light will be cancelled out. So it's not going to be rotating the Earth itself, where it can never get away from the sun. And this is very important because the telescope needs to be cold. And it needs to have this huge sun shield blocking all of that heat. So I'm not sure about whether the plans for these other telescopes to go to L2. I assume it won't be a problem. I'm sure there's smart people who have figured this out.
And I'll add to that, and we think of L2 as a dot on a diagram, but it's actually a pretty large area compared to the size of the telescopes, just like we actually now have thousands, and soon we'll have, unfortunately, tens or hundreds of thousands of satellites in low Earth orbit with the Starlink type satellites, and they don't crash into each other usually. So there's a lot of volume at L2 compared to the sizes of these instruments. And this person also asks if we can help them understand with some kind of analogy the differences between James Webb and Hubble. We talked about the size, which is one thing.
Yeah.
Right? The collecting area is about 10 times more.
Yeah, but
there are other differences.
Yeah, though the wavelength is going to observe that, and the instruments on it, I should add. So when we have a telescope, we reflect the lights into the instruments, but the instruments have to have some sort of detector or sensors. And in Hubble, these set detectors and sensors and instruments looked in the optical and the UV and then slightly the near infrared. But these ones in James Webb are going to be looking at the near infrared and mid infrared. So they're the actual instruments which are going to detect the photons, the light coming in, whether it's with an image or a spectra, are going to be looking at these longer wavelengths. And that's what's going to let us look further back into the universe. That's one of the main differences, I'd say, as well.
Yeah, and I'll add that the ability to see detail also depends on the size of the telescope. So when you're outside the atmosphere, the amount of detail you can see at a given wavelength scales directly with the diameter of the telescope. So this telescope is about 3 times as wide across as Hubble, so it will see 3 times finer detail. So if you want to see like the shape of a galaxy or the details of an exploding star, then that would be better with James Webb. Okay, any other questions, either in the chat on YouTube or, oh, here we have one. Oh, so we got to thank you. You're very welcome. Any other questions that Chris or I can answer for you? I do want to say, while we wait to see if anyone has questions, that the launch, of course, will be broadcast live everywhere. It is a very scary thing. There's something like hundreds of single points of failure along the way, because every little bit of the telescope that needs to unfold and lock. And if any of it fails, then we have a non-functioning telescope. So we know that, and unlike Hubble, it is not serviceable. Right? Yes. Hubble had a problem with its mirror shape, and we were able to essentially install corrective lenses inside because it was serviceable by the space shuttle. James Webb is not serviceable or upgradable. Actually, Chris, do you know what the lifetime of James Webb is?
Yeah, minimum, so 5 years, but they think they'll be able to do 10. So it's not even like Hubble, which can last as long. They think it's 5 to 10. Mm-hmm. It's minimum expected is 5, but hopefully 10 because it's an expensive instrument or telescope, sorry.
Okay, great. Well, if you want to join other people in watching the launch, NASA is hosting many launch parties online, and you can just Google JWST launch party and find opportunities to do it via Zoom or on YouTube or other virtual links. I'm assuming none of us are going to French Guiana, although that would be pretty amazing. Pretty challenging to get through the COVID protocols, I'm sure. Okay, if we have no more questions, then I will say mahalo again to Chris for the talk and to all of you for joining us. And we look forward to seeing you at other future events. If you are in Hawaii, and if the weather cooperates this weekend, then I invite you to the Bishop Museum on December 11th and 12th is having the 60th anniversary of its planetarium. And we'll be participating in that a bit with some activities outside, and there'll be a whole host of activities there in honor of that anniversary. So come and join us. Okay, if that's it, then I'll say thank you again, and we'll end the show. Thank you.